Hello class, welcome to our second lesson dealing with section 3.3, which deals with measures of variation. Today we're going to kind of cover again standard deviation and some things about it. There's also a topic called coefficient of variation that has a specific formula, so you want to make sure you pay close attention to that, as that'll be coming up on your homework and your upcoming test. Okay, so just a few things about standard deviations to review. First thing, we consider something unusual in general if it's more than 2 standard deviations away from the average or the mean. And when we compare data sets, we have to make sure that the data sets have the same units and they have similar means. Okay, if those two things aren't the case, then it's probably hard to compare the two data sets when it comes to variation, because the mean itself will affect kind of where the data is located anyway. When we looked at yesterday's lesson, we talked about the bell-shaped curve and how 95% of the data is within 2 standard deviations. That only works if it's a bell-shaped curve. If it's not a bell-shaped curve, we can still have an idea about how much data is within so many standard deviations, but we have to use what's known as Chebyshev's theorem. And it's just this formula right here, 1 minus 1 over k squared, where k is a number, and that's how many standard deviations. So if I want k to be 2 standard deviations, I would plug in 2. 1 minus 1 over 2 squared is 1/4, and that's 75%. So no matter what the data looks like, 75% of all data will be within 2 standard deviations. Notice, if it was bell-shaped, it's 95%. If it doesn't know if it's bell-shaped or if it's not, then it's only 75%. If I take that to 3, if k equals 3, it's going to be up to 88.9% within 3 standard deviations if I plug in 1 minus 1 over 3 squared. So when you're looking at this situation, what you want to make sure of is a bell-shaped curve? If it is, then you can use the 95% for 2 standard deviations. If it's not a bell-shaped curve, then you're stuck with like 75 for 2 standard deviations. Obviously, you could keep this going and make it 4 standard deviations, 5, etc., as you keep moving up in the number of standard deviations using k. Okay, the coefficient of variation is meant to describe standard deviation comparatively to how much of the mean it is. So it's just a division and make it a percent. If this idea is helpful if the means aren't the same, or the scales are different, or the units are different, which was some of the downfalls of standard deviation we talked about at the beginning of the lesson. Essentially, the higher the coefficient, the more variation there is. Okay, so if one has a coefficient of variation of 25, the other has a coefficient of variation of 75, then the 75 is going to be a higher kind of amount of variation compared to it. But you can kind of think of them as whichever number's higher has more variation. If they're close, they have about the same variation. And so it's simply just the standard deviation divided by the mean times 100. Notice this is for a sample, uses S and X bar, or sigma and mu for the population. The formula is the exact same. Okay, so here's some information about crashes of cars traveling at 10 miles an hour. It talks about the damages done to the cars. And then when we find the results, the question is $10,000 going to be an unusual amount to have to pay for damage done for a car traveling 10 miles an hour. Now, all I did with this data is plugged it into StatCrunch. So for your homework, there should be, with the data set, should be kind of a little box up here in the corner. You should be able to click that and say open in StatCrunch, and it should, boom, move it over right to StatCrunch. The other thing that you'll notice is on some testing situations, it's hard to use StatCrunch at times to be able to find your answers. So most likely what I'm going to do is probably make a screenshot of maybe some of the info from StatCrunch. So it'll kind of be balanced that way. But make sure you know how to use StatCrunch and how it represents data as you're looking at it. So plugging that all in, I get a mean of 6,901, about that much money, and the standard deviation of about 2,500, or just over that, 2,561. To be considered usual, it's the mean plus or minus 2 standard deviations. So that's what this is representing. One way to write that answer is this. And then if I actually have to find the lowest and the lowest and highest kind of limits to what would be considered usual, I would just plug this in my calculator. The 6901.33 minus 2 of the standard deviations, and then do the same with plus. I would double check that you're finding these numbers with your calculator correctly. And then what it means is any number that you give me, if it's within that realm, I'm going to say, nope, that's not unusual. So as the question is 10,000 unusual, the answer is nope, not unusual, because it's within the realm of 2 standard deviations. What this comes down to is what type of car did you hit. Okay, so it's not the speed that may affect how much money it costs to fix the car. It's what car did you hit. So that's why 10,000 would not be considered probably an unusual number in this case. Okay, for this question, we're looking at the coefficient of variation for Chase and Key Bank. The goal here is that we have to find the mean and standard deviation of both. Okay, so here's Chase Bank. I just plugged it in StatCrunch and did one of our stat summary stat columns. I get a mean of 4.36 and a standard deviation of 2.54. For Key Bank, I got a mean of 4.34 and a standard deviation of 1.18. And I just take the mean, the standard deviation divided by the mean times 100, standard deviation divided by the mean times 100, and I get 58.26 at Chase, 27.19 at Key Bank. What this means is no matter what, if the data was similar or not, there's more variation in the Chase Bank because this is a much higher number than the Key Bank one. Now, what's nice in this case is that the means are about the same. Look at this, 4.36, 4.34. They're almost identical, which means all I would have to do is look at the standard deviations, and this standard deviation is much higher compared to this one, especially because this is number of minutes you're waiting. Okay, so this would be true if you go to certain restaurants or drive-thrus or the bank, for example. You know certain places, you don't know how long you're going to have to wait. I know I've been to a few drive-thrus that if I don't see a line, it doesn't matter really because I don't know how long I'm still going to wait. Whereas certain places I know once I get in line, I know it's going to keep moving or I know how slow it's going to be. That's kind of what this is saying. So Key Bank's much more consistent with how long you're going to wait. Chase Bank, you could be there for a while because someone may have a longer question. There may be a longer line. Maybe there's more customers there. So you don't know how long you're actually going to have to end up waiting. That's what the coefficient of variation tells us. If one is much different than the other, the one with the lower has less variation. The one with the higher would have more variation in comparison to the two data sets. Okay, the heights of men, bell-shaped curve, that's important. Okay, so a bell-shaped curve and the mean of 172 and a standard deviation of 8. If you look here, I've got 164 and 180. And so what you want to do for these questions is start with 172 and add 8 and see if it gets you to the point. And if you take 172 plus 8, that gets you to 180. So this is plus or minus 1 standard deviation. If you go back to the bell-shaped curve stuff from the other day, then that should be 68% of the data is within 1 standard deviation. If you add 8 again, so 172 plus 8 is 180, plus another 8 is 188. That's 2 standard deviations. And if you do x bar plus or minus 2 standard deviations, that would give you 95% as your answer. And that comes out from the fact that it was 2 standard deviations plus or minus, and 95% of a bell-shaped curve would be within 2 standard deviations. If they didn't tell you bell-shaped curve, you have to use Trebuchet's theorem, which is the 1 over k idea. You shouldn't have to keep solving that. 1 standard deviation, if we go back to that real quick. Okay, 1 standard deviation was 75%. 2 standard deviations, is 75%. And 3 standard deviations is 88.9%. So here are the rules for normal distribution again. So just remember that you want to have these 3 definitely written down somewhere. So within 1 standard deviation, 68%, within 2 is 95, and within 3 is 99.7, which is almost all of the data at that point within 3 standard deviations. Okay, SAT scores have a mean of 1026 and standard deviation of 209. Now, they don't say anything about the data being a bell-shaped curve. Now, if you know anything about SAT scores, they're designed to be a bell-shaped curve, so that's why they're so useful and why the numbers work out the way they do, is because every single time it's going to be a bell-shaped curve, and statisticians can tell you exactly what numbers mean what thing. From Trebuchet's theorem, though, within 2 standard deviations, remember, 75%, so that would be the 1026 plus or minus 2 of the 209s. And remember, if you want to find those numbers, you got to find that yourself. And then within 3 standard deviations would be the same thing, but times 3 of the standard deviation, and that would give you 88.9% of the data. Okay, this question here is the only scenario where you're going to have to find standard deviation by hand. Okay, every other scenario, you're going to be able to use StatCrunch and find it. This idea is going to show up from time to time. They give you n, they give you sigma of x, and they give you sigma of x squared. They give you these numbers, and all basically I'm telling you to just plug it into this formula. Okay, so you got n right here, so that's n. Sigma x squared, that's the 72,000 number, minus sigma x, that's the 1,300 number, and square it. Then divide it by n times n minus 1. You should get a standard deviation of 20.74. Don't forget variance is that number squared. Okay, StatCrunch doesn't even give you that, so you got to make sure you can find the variance. Okay, and that would be 430.15. So when we're dealing with this scenario, you got to make sure Am I finding the right answer? Am I finding the standard deviation right? Okay, you have to be able to plug those numbers in, double check that. Hopefully I plugged everything right. The most common mistake is you don't put the numerator in parentheses and the denominator as a whole in parentheses and then take the square root of it. If you're struggling to get an answer, my suggestion would be to wait to do the square root until the last moment, and that might help you get an answer for this scenario. Okay, that's everything we have for section 3.3. I know that's a lot of new information for you, but you're going to want to make sure you know how to do coefficient variation, that last slide with dealing with finding standard deviation from the formula, and be able to compare data using the coefficient variation and figure out if something's usual or unusual with the two standard deviation approach for a bell-shaped curve. And don't forget about Chebyshev's theorem when it's not a bell-shaped curve. Have a good day, everyone.